All right, good morning. Okay, let's try that again. Good morning. Good, much better. So today we're going to be looking at the first part of section 3.4. It's a pretty important section. We're going to spend 2 days on it. We'll look at the first part of it. Almost everything we do from this point on is going to have the chain rule involved. So again, this is a critical section. Make sure you really spend time and effort to understand what's going on here. So to start looking at the chain rule, let's look at a problem such as this function. We'll make a simple one, 3x plus 5, the whole thing squared. Now, as usual, let's try to find the derivative of this thing. We've got a couple different choices here. One thing we could do is to rewrite it as 3x plus 5 times 3x plus 5. Then from this point on, I got two options. I could use the product rule. First and second and all that stuff. That's fine. Perfectly fine. The second option is to multiply this out first. Then take the derivative. Now, you know when you multiply this out, you're going to get polynomial terms added to or subtracted from each other, and that's very easy to handle. So here, let's use the second option here. The first option is perfectly fine, but we'll use the second option. So we get 9x squared plus 30x plus 25. So very clearly, then, simply, we can find y prime is 18x plus 30. Okay, nothing wrong with what we did here, perfectly fine. But notice that the only reason this could be done was because this power was not very high. If this were 3, we could still handle that somehow. 4 may be okay. 5 and beyond, things start to get very, very murky. And what if this thing is negative or a fraction? Then what we did here is not going to work. So then the above method is not going to work. At least easily. For instance, if we're looking for y is equal to 3x plus 5 to the 17th, and we're asking for a derivative of this thing, you could write this thing out 17 times and multiply it out 17 times. It's doable, but it takes a lot of time. Obviously, it's not going to be a very practical way to do things, right? So we've got to look for a different method. And that's where the chain rule comes in. The idea behind the chain rule, let me rewrite the function we're looking at. The idea behind the chain rule is to look at this function as a composite function. A composite function is a function within a function using a function as an input. So one way to do that is we can look at this thing as some function f using some other function g as its input. So the function takes g as an input as opposed to taking just regular x as an input. And in this case here, we're going to say that g of x is equal to 3x plus 5. And then the other function f, is going to take a different input. We'll call that u. And notice what happens to the function f here. F is going to take whatever g gives to it and raise it to the power of 17. And g, first of all, is if you feed an x into this function, the inner function, the g function, multiplies that by 3, adds a 5 to it, and then what comes out gets passed on to f. F then looks at whatever comes out and raises it to the 17th power. So this is the inner or the first function. It's the first function because that's what happens first. If you make up your mind what x is going to be, the first thing that's going to happen is that 3x plus 5. That's the inner function. And then what comes outside, the last thing that happens is the power of 17. Another way to look at what's going on here you decide what x is going to be. And the function g is 3x plus 5. And g is going to operate on the x you put in here and output something called u, which is 3x plus 5. Right? And that thing gets fed into the second function. The function is going to see whatever comes in, operates on that, and what it does is it just raises whatever comes in to the power of 17. So that's where we eventually get 3x plus 5 to the 17th power. Okay, now finding the derivative, looking at this thing here is going to give us some clue on how to find the derivative. Let's look at y prime in the Leibniz notation. In this notation here, this is asking us how does y change as x, which is this guy down here, as x changes. That's one advantage of the Leibniz notation. It explicitly spells out how does one thing change as a response to something other thing changes. If I change x over here, how does that propagate down this string, eventually affecting y? So, again, let's look at the Leibniz notation. We know the derivative comes from some kind of limit and the limit we take is the slope. The slope is dy over dx. Oops, sorry about that. Maybe we can fix that to mean something later. But this is what derivative tells us, right? The limit of delta y over delta x as delta x goes to 0. That is how we get the derivative. Now here, we're going to add a couple things to this. I want to rewrite delta y over delta x as delta y over delta u times delta u over delta x. And I'm allowed to do that because I haven't changed the function. I haven't changed the expression at all. I simply divide it by delta u and then multiply it back. We do that with rationalizing stuff, for example. We do that all the time. The important thing about the expression like this is, now we can look at these two parts. Delta y over delta u, this tells us how y changes as u changes. Just the second part of this string here. This is how y is affected by u. Okay? So that expression here really doesn't care about what x is doing. All it cares is how u is changing and how that then propagates down and affects y. And this right here tells us the first part of the story, how u is affected by some change in x. Okay, so what this ends up being is, I'll write this on the next page. Making this bad, sorry. As delta x goes to 0, then delta y over delta u turns into dy du, and then delta u over delta x turns into du dx. So from the last page, after the limit process is completed, delta y over delta u is dy du. This is the derivative of y with respect to u. Just the second part, the outer function by itself. And then this second part here is the derivative of u with respect to x. With respect to just means you're using that thing as the variable. So this part here, we only care about what y is doing with u, and here is what u is doing with x. Separate stuff. In the prime notation, if you had written this as f as a function of g of x, then the derivative, the equivalent statement to the above one is f prime of g of x times g prime of x. Okay? All right, these don't mean much unless you know how to use them. So let's practice using these things. Let's revisit the one we handled differently at the beginning. So this way we can compare the answer we got using the chain rule to the answer we got earlier doing something else. Okay? So first of all, let's call this thing inside, the inside function, the inside group, we'll call this thing u. So u is 3x plus 5. Now you write the outside function, what y is doing to this group of things you call u. Y is just looking at that thing, u, and then squaring that. So that's y. Y is u squared, and x is 3x plus 5. Taking the expression from the last page, the chain rule says the derivative of y with respect to x is how y is changing with respect to u, dy du, times how u is changing with respect to x, du dx. When you find dy du, you simply look at this line right here. Dy du is 2u. Du dx, you look at that line by itself. Derivative of this with respect to x. The 5 doesn't matter. The 3x reduces to a 3. So we end up getting 6 times u, or 6 times 3x plus 5, or 18x plus 30. Which is, of course, the same thing. Okay. Earlier, we multiplied this out and took the derivative of the resulting polynomial, and we got 18x plus 30. Here, we got the same thing. So now, even if the power goes to a ridiculous number, like 17, for example, once you know how to handle one power in this form, you know how to handle any resulting power. You again interpret the inner function as u, and the outer function as u to the power of 17. So we end up getting y prime equal to dy du, du dx, and once again, you look at these two things individually for each of these two parts. Dy du, just this line right here, that will be taken care of by the other thing. Just this line here gives me 17 times u to the power of 16. And then du dx, now we look at the inner function part. U is a function of 3x plus 5. Derivative is simply 3. Okay, now look at these two things here. I want to point out something that's worth noticing. Question? Guys, question? Doing okay? Figured it out? Good. Okay, so if you look at this thing right here, look at the derivative. Look at what happened here. It seems like what we ended up doing is we brought the power down. Keep that thing the same, reduce the power by 1. What does that remind you of? The basic power rule, right? And this extra 3 here is the derivative of this thing. So this part is the same as the power rule. This part right here resembles the basic power rule. If 3x plus 5 is, quote unquote, the x in the power rule part. If this were simply x to the 17, then it's 17 times x to the 16. Here we did something very similar to that. We pretend that that's just x. Brought the power down, reduced power by 1. And then we tack on this extra part. this ends up being to account for the fact that 3x plus 5 is not x. Okay, so another very useful version of the chain rule here is if y is equal to u to the power of n, where u is some function of x, then y prime, according to what we just discovered here, is n times u to the n minus 1, the same thing as the classical power rule, times, now we account for the fact that u is not just an x anymore. And that comes from the derivative of u, du dx. This is exactly the same thing as the two other things on the last page. They're using different kinds of packaging and different kinds of expression, but they all tell you exactly the same thing. You take the derivative of what's inside, this guy right here, and then how the outer function is affected by that inner function. Let me give you another example where that's very useful. Y is the fifth root of 4x squared plus 5. We'll rewrite it as 4x squared plus 5, the whole thing raised to the power of 1 over 5. This is a situation where you cannot multiply anything out. How do you multiply this out by 1 over 5 times? That cannot be done algebraically. The only way to handle an expression like this is the chain rule. There's no other way to do it. Okay, so that last expression, last form of the chain rule that we looked at on the last page, if y is some function u to the power of n, what we got going on here, y prime is, bring the power down, keep that u, reduce the power by 1, and then the derivative of u to account for the fact that this is not just a plain old x. So y prime, therefore, according to the rule, bring the power down, keep all of that stuff, reduce the power by 1. So we pretended 4x squared plus 5 is just an x, and we got this thing. And now we have to account for the fact that it's not just an x. And therefore, we multiply by the derivative of this, and we get 8x. Okay, so that's the derivative. All right, does that make sense, everyone? Okay, let's try another one. One over x to the fourth plus 1 to the power of 5. This one, we have a couple different options. One is to leave it as the way it is. The other one is to rewrite this in that form, u to the n. Remember, back when we started doing derivatives, we wrote everything in the form of x to the n. Same thing here. If you could write things in this form here, you know how to handle that. So that's the other option, is to rewrite it as x to the 4th plus 1 to the power of minus 5. So my options are quotient rule with this thing, or here I can use the chain rule. Okay, the second form is in this form, u to the n. Easy. This one is just in the classical chain rule form. Also not a big deal. Now, which one would you rather use if you're given a choice, quotient rule or chain rule? Yeah, I don't know about you, but I think the chain rule is probably a little bit easier. At least, I know, I personally really don't like fractions. If I could get away without doing any fraction, that would be great. So personally, I would go with the chain rule here. But there is really no reason why the quotient rule is wrong in any way. Okay, so let's try using a chain rule here. And you already know how to do it because the last example showed you how to do it. Pretend that's an x. Bring the power down. Keep all that stuff the same. Reduce the power by 1. And now you account for the fact that this is not just an x anymore. So we multiply by the derivative. And we get 4x cubed. We can write it that way, or we could write it, put it back in the form of a fraction. Either of these is fine. WebAssign would take either of these. Probably would even take that. It doesn't seem to be too picky with simplification most of the time. Okay, does that make sense? Any question on these examples? Okay, now this rule actually is also very useful. Sometimes when you have trig expressions that can be put in that kind of form. For example, if you're looking for the derivative of cosine of x to the 4th power, the rule we apply for the last two examples can still be used here directly. You just got to realize that the way we write trig powers is kind of funny. This 4 with a cosine actually means cosine of x to the power of 4, right? That's what it means. The 4 goes with the cosine of x, not with the x. So now notice what we got here is in the form of u to the n. And we know how to handle u to the n. We pretend u is an x, apply the power rule, and then we pay for the fact that u is not just an x. So we get, pretend that's an x, bring the power down, keep whatever that thing is the way it is, reduce the power by 1. Okay, now we account for the fact that that thing is clearly not an x. So we multiply by the derivative of that. Right? So we get this. Once again, pretend that's an x, bring the power down, keep that the same, reduce power by 1. Now you multiply by derivative of that to account for the fact that it's not just an x. So slight simplification here. What do we get? We get minus 4 cosine. Let's put a 3 back with the cosine, and then the sine here. Questions? Okay, now let me make a change to that. Just a very, very brief, very, very minor change, but actually a very, very major change in terms of the derivative. So all I'm going to do is to move that power 4 to go with the x. This time, what this means is that we have the function cosine of x to the 4th. The power of 4 goes with the x as opposed to cosine of x. So be very careful with how we write trig powers. The 4 with the trig function means this. The 4 with the variable means cosine of that thing. Now here, let's go back to the first version of the chain rule we saw. All right, so the first version of the chain rule, where the heck? Here, this guy right here. Identify the inside and the outside function. So let's call this thing u. And so what we got here is u is equal to x to the 4th. The way you identify the inside and outside functions is, like I said earlier, if you were choosing a number for x, what is going to happen first? If I want x to be 2, for example, the first thing that would happen is I would raise it to the power of 4. So that first process that's going to happen, that's the inside function. First thing to happen if you have chosen x as a number. The first thing that you would do if x is a number, that is your inside function. And then the outside function y is usually very easy to figure out. What is y doing? Y is going to take the cosine of whatever you just did. So that would be cosine of u. Does that make sense, everyone? Okay, good. All right, so then let's take the derivative. Y prime dy du. How is basically you got two things here. Derivative of these two functions depending on its own variable. We have two functions, y using u as a variable. That's what this is. How is y affected by its own variable? Even though u really depends on x, now we just look at these two things one stage at a time. How is this going to happen? What's going to happen when u changes? This guy tells us that. What's going to happen to u when x changes? So that's du dx. So what do we get? We get minus sine of u times 4x cubed. Okay, then the last thing you want to do is just to simply sub in what u is equal to. And I'm just going to tweak this a little bit. Let me put this in front. I'll write it as minus 4x cubed times sine of u, where u is x to the fourth. Okay, big difference. The moving that one power, you change the meaning of that function completely. This one is cosine of x, the entire thing to the power of 4. This is cosine of just that x to the fourth power. The derivatives are clearly not the same. There's some similarities here and there, but clearly not the same thing. Okay, if that last example makes sense, then you should have no problem handling this one right here. You got 1 minute to find the derivative. Go. Okay, time's up. That's not 1 minute, but close enough. What's the derivative? Who has an answer? Okay, everyone agree? Okay, so this is what he got. Y prime is, you said 2 cosine of 2e to the power of x times e to the power of x. Okay. Who got that? Good, good, wonderful. If you didn't get that, let me quickly go over this thing here. Remember, identify the inside function. The first thing that you would do once you've chosen a number for x, if I've chosen x to be 3, for example, the first thing I would do is raise e to that power and multiply by 2. So that's my inside function. Once I've identified that to be my inside function, y is just the sine of that, sine of u. So this is very, very similar to what we did in the last example. Then you multiply together the derivatives of each of these two things with respect to its own variable. First derivative of sine of u is cosine of u. Derivative of u du dx is 2e to the x. And then we change things up a little bit, moving things around as needed. These are all multiplied, so you can move things around however you want. And so there we go. Okay, good, good. Now let me tweak this function just a little bit. Let's do this. E to the power of 2 sine of x. What would you let u be? 2 sine of x? Does that make sense? That's the first thing that you would do once you decided x to be pi over 2, for example, right? So we'll let that be our u. What about y then? E to the u? Y is usually very simple once you've decided what u is going to be. is simply a consequence of that decision by looking at your original function, come up with y. All right, so y prime, the derivative of y with respect to its own variable, the u variable. Derivative of u with respect to its own variable. What's dy du? E to the u, right. That's a nice thing about e. What about du dx? Positive or negative? Positive, good. 2 cosine of x, right? So finally, we get 2 e to the u times cosine of x. Questions? Does that make sense to everyone? All right, let's do one more. And then we'll look at the derivative of exponential where the base is not e. So one more here before we look at that. This one. Let's do derivative of e to the power of e to the x. How would you pronounce this? X, maybe? That's a joke. Thank you, thank you. That makes me feel very good about it. Okay, now look at this. All you got to do is identify the inside function and the outside function, and then you know what to do, right? The fact that this looks so complicated really doesn't change anything. All this is doing is raising e to the power of e to the x. This is fundamentally no different than the last example. Last example, e had a power of 2 sine x. We took care of it. This one is exactly the same thing, the power being something else. Identify what's on the inside. The first thing that would happen once you've decided what x is going to be. And then y, the outside function, is a consequence of that choice. Y is e to the u. So y prime dy du, du dx. Derivative with respect to its own variable, right? Dy du, of course, is e to the u. Du dx, of course, is e to the x. Then lastly, get rid of u. And there we go. Okay, you can handle e to the, as complicated as a power as you want it to be. As long as you know the derivative of e and you can somehow identify the inner function, you're fine. Perfectly fine. All right, so we know the derivative of e to the x is e to the x. But remember, this is only true because e is such a special number that it is a number defined essentially, so this happens. If the base a here is not equal to e, then the derivative in general is not going to be itself. E is a number defined such that this happens. So we're going to figure out what is the derivative of a to the x. Okay, so what do we do here? We're going to make use of the fact that if we know this, we can always do stuff like that to make things work, right? If you know this, then the next thing to do is to somehow write a to the x as e to the something. If I can rewrite the expression a to the x as e to something, then you know what to do. Regardless of how complicated the exponent is, we have a rule for that. So that's the key here. So, remember the fundamental property between natural log and e. We know that e raised to the power of ln of x is just going to reduce to x, whatever that x is equal to. If this is true, then I can change x to anything I want. So e to the power of a to the x must also be a to the x. Right? If this is true, x is simply a variable, a placeholder. If I change x to anything else, that expression still has to hold. So there's our first major step here, a to the x rewritten as e to the something. We can simplify this even more. We're allowed to bring that power, which right now is x, to the front because of the properties of log. So I brought this power x to the front here. So this is going to be e to ln of a times x. The important thing to remember is that this is a constant. That thing is a number. So this expression here is fundamentally the same as e to the 2x, for example. E to a number times an x. Therefore, derivative of a to the x is the same as the derivative of e to the power of ln of a times x. That again is the same as the examples we've been doing. If you let y be e to the ln of a, that's a number, remember, where u is equal to ln of a times x, and y is e to the u, just like the last example, then y prime dy du, du dx, is e to the u times, what's the derivative of u now? What's du dx in this example, in this situation here? Remember, ln of a is a number. What's the derivative of 2x? What's the derivative of 3x? So what's the derivative of ln of a times x? Yeah, ln of a. It's a number. It's a number that's no different than the number 2, the number 3. That's a number. So this is going to be equal to e to the u. What the heck is u? This guy, right? ln of a x times ln of a, right? Hey, but look, this, if I just do the reverse of the things I did here, so this guy right here is this, which really goes back to that, which goes back to this. So that thing I circled in green really is just a to the x times ln of a. So now, therefore, the derivative of a to the x, after all of that, we found out it will be a to the x times ln of a. Does that thing in the box work if a is equal to e? Do we get what we expect? We do, right? Because e to ln of e is 1. So if a happens to be e, we get what we expect. Derivative of e to the x is e to the x. Okay, that's it. See you Friday.